at this point, the Fluent solver knows what is the mathematical model we want to solve. Okay, so it knows this. So let's get it to solve that, the governing equations and boundary conditions numerically using the finite volume method and calculate the selected variables. So we looked at the 5 variables that need to be computed at each cell center. So let's get it to do that. I'll go under solution, and under solution methods, there are lots of knobs in the solver settings that one can tweak to get the numerical solution. Here I'm trying to tweak as few as possible, and as you get more into CFD and Fluent, you can explore all the other knobs that one can twiddle as one goes to more and more complicated problems. The only thing I'll change here is I will change the discretization on momentum to first order upwind, and don't worry about upwind. That affects how the cell center values get interpolated to the faces. So the first order, so I've decreased the accuracy. The discretizing accuracy is first order. That means if I make my mesh half the size in both directions, my error will go down by a factor of 2. The advantage of the first order is that the iterations tend to be more stable. So it's like first order is less accurate, but it's more stable. Second order is more accurate, but it's less stable. So I like to usually start off the iterations with first order and then kick it to second order once I get my initial convergence with the first order. So that's what I'm going to do here. And by default, it's set to first order for Kn, the epsilon equations. I won't twiddle any of the knobs under solution controls. I'll go to monitors, and if I look at the residual setting, it's of the order of 10 to the power of minus 3. Let's leave that for now, with the understanding that ideally we would like to be drop that below 10 to the power of minus 6, but we can come back to that. Like I mentioned in the laminar pipe flow tutorial, it's also good to monitor an additional quantity. Drag is a good one, so we'll monitor that, and we'll also monitor the lift, because the two entities that we're really interested in are the lift coefficient and the drag coefficient. Let's set up monitors for that so that we can see how they change as the iterations proceed. So I'll say create. Let's do lift first. And to understand what to set here, let me go to a previous PowerPoint slide. This is from the pre-analysis. I have annotated it to explain what we need to enter here. What we want the solver to do is to integrate the pressure and the shear, the normal force and the tangential force on the airfoil surface around the airfoil. And if it take the component perpendicular to the free stream, that is by definition the lift. So if the airplane, this is the direction in which the airplane is flying, so the lift is perpendicular to that direction. So we want the integration to be over lower and upper, so that will do the integration over the entire airfoil. I'll leave the default name, and as we did before, print to console, plot, write is a good idea. And this is telling me, okay, in which direction do you want it? The component of this force on the airfoil, and we want it, if the angle of attack was 0, that is right, but we have to tweak this, modify this, because the angle of attack is not 0. So the component in the y direction is cosine alpha. That's going to be 0.9848. And in the x direction of the normal vector, it's going to be sine alpha, and it's going to be negative because the lift is tilted back. So minus 0.1736. So that'll give me the force in this direction. And I'll say OK. And that'll, so I've set up, now it knows how to calculate the lift, and then I have to tell it how to non-dimensionalize it. That I do under reference values. and I need to make sure that I enter, the right values for rho, v infinity, and so on to use in the non-dimensionalization. This is not going to affect anything else in your solution. It's only going to affect, post-processing of non-dimensional quantities. I think I've mentioned before that I've seen students get confused about it. And I will use a shortcut. I'll say compute from far field 1, and it'll enter, whatever values we entered here into, it'll enter into all these boxes. The ones we are interested in is density, so it's entered the density. The velocity scale, which is the free stream velocity, so it got that from the components that we entered. And then it needs this, which you enter here. That's a planform area. That's the area looking from the top, and we assume a unit span in the direction perpendicular to the screen. So that's 1. So that'll give me the right lift coefficient. Similarly, let's set up a monitor for the drag. So I'll go and say create drag, same thing. So it's the same vector, but it's the same kind of calculation, except that we want the component in the direction of the free stream. So that's since drag is a force that opposes the direction in which the airplane is flying. So that's going to be cosine alpha, which is 0.9848, and the y component is going to be 0.1736. And we already set up the reference values. The non-dimensionalization is the same, so we don't need to redo that for the drag. So we have set up for iterating, and let's go ahead and iterate, get the solver to iterate and find, a solution to our governing equations and boundary conditions.